Our moon moves away from Earth by about the width of a fingernail each year. It's a departure so gradual you'll never notice it in a lifetime. But it's been happening since the moon first formed over 4 billion years ago. Back then, our companion was much closer, looming large in the sky and making Earth's days just a few hours long. The moon's slow retreat is caused by the same tidal forces that pull our oceans back and forth. As Earth spins beneath the tidal bulge, energy is transferred to the moon, gradually pushing it into a higher orbit. This gentle separation will continue for billions of years, until eventually Earth and Moon become tidally locked, always showing the same face to each other like cosmic dancers frozen in an eternal embrace. Some moons are older than the planets they orbit. In the outer reaches of our solar system, where ice and rock mingle in the cold, astronomers have discovered moons that tell ancient stories. These captured wanderers likely formed elsewhere, drifting through space as lonely asteroids or small planets until they were gently caught by the gravity of larger worlds. Their surfaces bear scars from a time before their current homes even existed, cratered landscapes that remember impacts from the early days of the solar system. Jupiter and Saturn both host such ancient companions, small, irregular moons with tilted orbits that hint at their foreign origins. They are cosmic immigrants, carrying memories of distant birthplaces in their silent, tumbling dance around alien suns. Titan has lakes of liquid methane under orange skies. Saturn's largest moon exists in a world so strange it might have been imagined by poets. Beneath its thick, hazy atmosphere lie lakes and rivers filled not with water, but with liquid methane and ethane. These hydrocarbons flow across Titan's surface like oil, pooling in vast, smooth basins that reflect the dim light of the distant sun. The sky above glows orange through the methane haze, and gentle rains of liquid methane fall from hydrocarbon clouds. It's a complete weather cycle, just like Earth's, but made of entirely different substances. Titan's surface pressure is slightly higher than Earth's, and its gravity is low enough that if you could somehow survive there, you could flap your arms and fly through that thick orange sky like a bird. Europa's ice shell hides an ocean deeper than all Earth's seas combined. Beneath the frozen surface of Jupiter's fourth largest moon lies one of the most intriguing secrets in the solar system. Europa's shell of ice, though many kilometers thick, floats atop a global ocean that may contain twice as much water as all of Earth's oceans put together. This hidden sea remains liquid because of tidal heating caused by Jupiter's immense gravity, which flexes and stretches Europa as it orbits. The ice above shows signs of this hidden ocean, cracked and ridged like a frozen pond that has shifted and refrozen countless times. Some scientists believe this dark ocean, warmed by geological activity and protected from space radiation by the ice above, might harbor conditions suitable for life. It's a water world disguised as a frozen moon, keeping its deepest secrets locked beneath a crystalline shell. Our moon was born from a collision that nearly destroyed Earth. Long ago, when Earth was young and still glowing with the heat of formation, a Mars-sized planet called Theia struck our world in a glancing blow. The impact was so violent, it vaporized both the impactor and a large portion of Earth's surface, flinging molten rock and metal into orbit. This debris cloud, hot and chaotic, gradually coalesced under its own gravity to form our moon. The evidence for this dramatic origin story is written in the very rocks the Apollo astronauts brought back, which show that moon rocks and Earth rocks are made of remarkably similar materials. Our gentle companion in the night sky is actually the child of catastrophe, born from fire and collision, now shining peacefully down on the world it helped create. Some moons have their own moons. In the strange dynamics of celestial mechanics, a few large moons are theoretically capable of hosting their own smaller companions. Though we haven't discovered any natural examples yet, the physics suggests that moons like our own could capture tiny asteroids or debris and keep them in orbit. These would be submoons or moonmoons, small objects caught in the gravitational embrace of a larger satellite. The orbits would be complex and unstable, influenced by both the moon and its parent planet, creating a delicate three-body dance that might last only a few million years before the system either breaks apart or the objects collide. It's a reminder that even in the seemingly empty space between worlds, gravity weaves intricate patterns of motion and possibility. Io's surface is painted with sulfur from hundreds of active volcanoes. Jupiter's innermost large moon is perhaps the most volcanically active world in the solar system, its surface constantly renewed by eruptions of sulfur and sulfur dioxide. The landscape is painted in brilliant yellows, oranges, and reds, like an artist's palette left to dry under alien skies. These volcanoes are powered not by radioactive decay like Earth's, but by the constant gravitational kneading Io experiences as it orbits Jupiter. The giant planet's gravity stretches and compresses the moon's interior, generating enough heat to keep hundreds of volcanoes active at once. Some of these eruptions are so powerful, they shoot plumes of gas and particles hundreds of kilometers into space, creating a thin atmosphere and even influencing Jupiter's own magnetic field. Io is a world of constant change, where the ground itself is always being rewritten in fire and sulfur. Enceladus shoots geysers of water into space through cracks in its ice. Saturn's small moon, Enceladus, appeared unremarkable until spacecraft revealed one of the solar system's most spectacular phenomena. Near its south pole, long cracks in the ice called tiger stripes periodically erupt with geysers of water vapor, ice particles, and organic compounds. These eruptions can reach hundreds of kilometers into space, feeding Saturn's E-ring with fresh material. The geysers suggest that beneath Enceladus's frozen surface lies another hidden ocean, kept liquid by tidal heating from Saturn's gravity. The water that shoots into space carries traces of salts and organic molecules, hinting at chemical processes occurring in the ocean below. It's as if this small moon is breathing, exhaling the contents of its hidden sea into the vacuum of space in great crystalline plumes. Miranda looks like it was shattered and reassembled. Uranus's moon. Miranda presents one of the most bizarre landscapes in the solar system, a patchwork surface that looks like it was broken apart and haphazardly put back together. Ancient cratered terrain sits next to younger, grooved regions in a chaotic jumble that defies easy explanation. Some areas show parallel ridges and valleys that stretch for hundreds of kilometers, while others display the random pockmarks of ancient impacts. One theory suggests that Miranda was indeed shattered by a massive collision early in its history, then slowly reassembled under its own weak gravity. Another possibility is that the strange terrain results from unusual heating patterns in the moon's interior, causing different regions to evolve at different rates. Either way, Miranda remains a puzzle written in ice and rock, a moon that wears the evidence of cosmic violence on its fractured face. Triton orbits Neptune backward and is slowly spiraling inward. Neptune's largest moon is unique in the solar system for its retrograde orbit, meaning it circles its planet in the opposite direction from Neptune's rotation. This backward dance is a sign that Triton was likely a captured object, perhaps a dwarf planet from the outer solar system that wandered too close to Neptune's gravitational embrace. The same forces that captured Triton are now slowly pulling it closer to Neptune. In about 1 billion years, the moon will cross what's called the Roche limit, the distance at which tidal forces overcome the moon's own gravity. When that happens, Triton will be torn apart, its fragments forming a spectacular ring system around Neptune that might rival Saturn's famous rings in grandeur. For now, though, Triton continues its lonely backward orbit, a captured wanderer counting down the eons until its spectacular final act. Some moons are shepherds that keep planetary rings in line. Among Saturn's many moons are tiny guardians called shepherd moons, small satellites that orbit just inside and outside some of the planet's rings. These moons, though barely large enough to be called moons at all, play a crucial role in maintaining the sharp edges of certain rings through their gravitational influence. Prometheus and Pandora, for example, bracket Saturn's narrow F-ring, their combined gravitational effects keeping the ring particles confined to a relatively narrow band. When ring particles drift too far inward or outward, the shepherd moons gently nudge them back into place through gravitational resonances. It's a delicate cosmic dance, where tiny moons weighing less than a large city asteroid keep trillions of ice particles organized across hundreds of thousands of kilometers of space. The largest moon in the solar system is bigger than Mercury. Jupiter's Ganymede holds the record as the largest satellite in our solar system, stretching over 5,200 kilometers in diameter. This makes it larger than the planet Mercury, though not as massive due to its composition of ice and rock rather than dense metals. Ganymede is also unique among moons for having its own magnetic field, generated by a partially molten iron core deep within its interior. This magnetic field creates aurorae at Ganymede's poles, ghostly curtains of light that dance in the moon's thin oxygen atmosphere. Beneath its surface, like so many of the outer moons, Ganymede likely harbors a subsurface ocean sandwiched between layers of ice. Despite its great size, Ganymede remains a quiet world, its ancient surface scarred by impacts and tectonic activity from billions of years ago. Deimos and Phobos are probably captured asteroids that will meet different fates. Mars's 2 tiny moons are irregularly shaped objects that look more like potatoes than the spherical satellites we're used to seeing. Deimos and Phobos are likely asteroids that were captured by Mars's gravity long ago, rocky remnants from the asteroid belt that now circle the red planet in low, fast orbits. But their futures are very different. Deimos, the outer moon, is slowly drifting away from Mars and will eventually escape its gravitational hold, returning to space as a wandering asteroid. Phobos, on the other hand, orbits so close to Mars that it completes an orbit in just over 7 hours, faster than Mars rotates. This proximity means Phobos is gradually spiraling inward, doomed to crash into Mars or break apart into a ring system within the next 50 million years. 2 tiny moons, 2 different destinies, playing out their cosmic drama in the rust-colored skies above Mars. Some moons are captured comets that have lost their tails. In the outer solar system, several small moons show characteristics that suggest they began life as comets. These objects likely originated in the cold outer regions where water, ice, and other frozen materials are common, at some point in their journey toward the inner solar system, where the sun's heat would have boiled away their volatile materials in spectacular tails. They were captured by the gravity of giant planets. Now they orbit as dark, irregular moons, their comet days behind them. Their surfaces are often very dark, coated with organic compounds that give them a charcoal-like appearance. These captured comets represent a kind of fossil record, objects that began one kind of celestial life and were transformed into another through the patient work of gravity and time. Hyperion tumbles chaotically as it orbits Saturn. Most moons maintain a stable orientation as they orbit their planets, with the same side always facing inward due to tidal locking. But Saturn's moon Hyperion defies this pattern with one of the most chaotic rotations in the solar system. Instead of spinning predictably, Hyperion tumbles end over end in an unpredictable dance, its rotation period varying from one orbit to the next. This chaotic behavior results from Hyperion's irregular shape and its orbital resonance with Saturn's much larger moon Titan. The gravitational tugs from both Saturn and Titan combine to keep Hyperion tumbling like a cosmic football, never settling into a stable spin. Its surface, meanwhile, has a strange sponge-like appearance, covered with craters that give it the texture of cosmic foam. Moons can have atmospheres thicker than some planets. While we often think of moons as airless worlds, several satellites in our solar system maintain substantial atmospheres. Titan's atmosphere is actually thicker than Earth's, composed primarily of nitrogen with a small percentage of methane. This thick blanket of gas creates weather patterns, seasonal changes, and even a greenhouse effect that keeps the surface warmer than it would be otherwise. Triton also has a thin but measurable atmosphere of nitrogen, maintained by sublimation from its icy surface as it slowly warms when Neptune's elliptical orbit brings it closer to the Sun. Even our own moon has an extremely thin atmosphere, technically called an exosphere, created by the solar wind interacting with lunar soil. These atmospheric moons remind us that the boundary between planets and their satellites can sometimes blur in unexpected ways. The moons of Uranus are named after characters from Shakespeare and Alexander Pope. Unlike other planets whose moons bear the names of Greek and Roman mythological figures, Uranus's satellites carry literary names that seem to whisper poetry across the cold void. Miranda, Ariel, Umbriel, Titania, and Oberon drift through space like characters from A Midsummer Night's Dream and The Tempest, their names as ethereal as their distant orbits. This naming convention began with William Herschel's son, who discovered the first 4 moons and chose to honor English literature rather than classical mythology. As more moons were found, astronomers continued this tradition, creating a celestial library where sprites and fairies, dukes and princesses circle their tilted world in the outer darkness. It's a reminder that even in the vast mechanical clockwork of the solar system, there's room for imagination and verse. Some moons glow softly in their planet's shadow. When a moon passes behind its planet and enters the shadow, you might expect it to disappear completely. But some moons continue to glow with a faint reddish light, illuminated by sunlight that has been filtered through their planet's atmosphere. This phenomenon, called atmospheric refraction, bends red wavelengths around the planet like light through a lens, casting a dim copper glow on the moon's surface. Earth's moon sometimes shows this effect during lunar eclipses, glowing like an ember in the sky. The exact color and brightness depend on the composition of the planet's atmosphere and how much dust or clouds are present. It's a gentle reminder that even in shadow, light finds a way to reach across space, painting moons with the filtered breath of their parent worlds. Charon and Pluto are tidally locked in a cosmic waltz. In the far reaches of the solar system, Pluto and its largest moon, Charon, perform one of the most intimate dances in space. Unlike most planet-moon systems, where only the moon is tidally locked, both Pluto and Charon always show the same face to each other as they orbit their common center of mass. This means that if you stood on Pluto's surface, Charon would appear to hang motionless in the sky, never rising or setting, a constant companion frozen in the star field. The same would be true from Charon's surface, where Pluto would remain fixed overhead. This double tidal lock is rare in the solar system, a gravitational embrace so complete that the two worlds have become synchronized dancers, spinning together through the cosmic dark with perfect, eternal timing. Moons can have seasons that last decades. Just as Earth experiences seasons due to its tilted axis, some moons undergo their own seasonal changes, though on vastly different timescales. Titan experiences seasons as Saturn orbits the Sun over its 29-year period, with each season lasting more than 7 Earth years. During Titan's northern winter, the polar regions become shrouded in a dark hood of hydrocarbon haze, while lakes of methane grow and shift with the changing weather patterns. Spring brings clearing skies and the migration of these liquid hydrocarbons from one hemisphere to the other. Summer illuminates landscapes that have been dark for years, revealing changes that occurred during the long winter night. These extended seasons create a slow rhythm of change that unfolds across human generations, a patient breathing of weather and chemistry beneath alien skies. Some moons are so small, they could fit inside a large city. At the tiny end of the moon spectrum are objects barely large enough to be held together by their own gravity. Mars's moon Deimos measures only about 15 kilometers across at its widest point, small enough to fit comfortably within the boundaries of a major metropolitan area. Many of Jupiter's and Saturn's smallest moons are even tinier, irregular chunks of rock and ice that would be lost among Earth's skyscrapers. These miniature worlds have such weak gravity that a good jump could potentially launch you into space, and their surfaces are often covered with loose debris that shifts and slides with each minor impact. Despite their diminutive size, they're still moons in every sense, complete worlds with their own geology, their own history written in craters and cracks across surfaces you could walk across in an afternoon. The ice moons of Jupiter sound like they're singing. The 4 largest moons of Jupiter, known as the Galilean satellites, are locked in a complex gravitational dance called orbital resonance. Io completes 4 orbits for every 2 of Europa and every 1 of Ganymede, while Ganymede completes 2 orbits for every 1 of Callisto's. This mathematical precision creates a kind of celestial music, a rhythm of gravitational tugs that has kept these moons in harmony for billions of years. The resonance prevents the orbits from drifting apart or becoming chaotic, maintaining a stable configuration that allows each moon to exist in its own unique environment. When scientists convert the orbital frequencies into sound waves, the result is a haunting chord that seems to echo across the vast spaces between worlds, a song written in gravity and time. Moons can steal material from each other across millions of kilometers. In the complex gravitational environments around giant planets, some moons can influence each other in subtle but measurable ways. Io's volcanic eruptions don't just affect its own surface. They also contribute material to Jupiter's magnetosphere that eventually finds its way to other moons. Europa receives a steady rain of sulfur particles originating from Io's volcanoes, painting subtle color variations across its icy surface. Even more remarkably, some of Saturn's moons appear to share material through the planet's ring system, with particles knocked off one moon eventually settling on another. This exchange of material means that the moons of giant planets aren't isolated worlds, but members of interconnected systems where the geology of one world can subtly influence the surface chemistry of its neighbors. Some moons have underground oceans that never freeze. Deep beneath the icy surfaces of several outer solar system moons lie oceans that remain liquid, despite being farther from the sun than any place water flows naturally on Earth. These subsurface seas are kept warm not by sunlight, but by the heat generated from tidal flexing as the moons orbit their massive parent planets. Jupiter's gravity constantly kneads Europa and Ganymede like cosmic dough, generating friction in their rocky cores that heats the overlying ice enough to maintain liquid water. Saturn does the same for Enceladus and possibly several other moons. These hidden oceans may have existed for billions of years, stable bodies of water larger than Earth's Mediterranean Sea, dark and warm beneath kilometers of protective ice, perhaps representing the most common form of liquid water in the galaxy. Moon dust behaves like both liquid and powder. The surface material on most airless moons has properties unlike anything we experience on Earth. Without wind or water to weather it, moon dust consists of tiny glass fragments created by billions of years of micrometeorite impacts. This dust has sharp, angular edges that make it incredibly clingy, adhering to spacesuits, equipment, and anything else it touches through electrostatic forces. At the same time, it flows almost like a liquid when disturbed, creating the smooth, flowing patterns visible in astronaut footprints and rover tracks. The dust is so fine that it can hang in the vacuum above the surface for hours after being kicked up. forming temporary clouds that drift slowly back down in the weak gravity. It's simultaneously powder and liquid, sharp and soft, creating landscapes that seem to flow like frozen water under the strange physics of airless worlds. Some moons experience earthquakes that last for hours. While we call them moonquakes rather than earthquakes, several moons in our solar system experience seismic activity that reveals the dynamic nature of their interiors. Our own moon has deep moonquakes that occur roughly every 27 days, triggered by tidal stresses from Earth's gravity. These quakes can last for more than 10 minutes, much longer than most earthquakes, because the moon's dry interior transmits vibrations more efficiently than Earth's water-bearing rocks. Europa likely experiences ice quakes as its shell flexes and cracks under Jupiter's tidal influence, while Enceladus may have quakes related to the eruption of its water geysers. These seismic events help scientists understand the internal structure of moons, revealing hidden layers, liquid regions, and the complex interplay between tidal forces and geological activity across the solar system. Captured moons often have the most eccentric personalities. The moons that formed alongside their planets tend to follow predictable circular orbits close to their parents' equatorial plane. But captured moons, those wanderers pulled in from elsewhere, often display wildly eccentric behavior. They may orbit backward at steep angles or in highly elliptical paths that take them far from their planet before swinging back in close approaches. These irregular orbits tell stories of cosmic encounters, gravitational captures that occurred when a passing object found itself moving just slowly enough to be trapped, but too fast to settle into a neat, circular orbit. Many of these captured moons are also unusually dark, with surfaces that reflect less light than charcoal, suggesting they originated in the outer reaches of the solar system where organic calms, pounds, and water ice created their distinctive coloring. The shadows on some moons are deeper than the deepest caves on Earth. In regions where the sun never shines, such as the bottoms of deep craters near the lunar poles, temperatures can drop to among the coldest measured anywhere in the solar system. These permanently shadowed regions, sometimes called cold traps, can be colder than the surface of Pluto, reaching temperatures as low as 25 Kelvin. In these shadowy depths, water ice can remain stable for billions of years, accumulating like frost in an eternal winter. Some of these shadowed areas have remained dark since the moon formed, creating pockets of primordial ice that preserve a record of water delivery to the inner solar system. NASA has even detected water ice in these lunar shadows, deposits that might one day provide resources for future explorers of these perpetually dark and silent valleys. Moons can create their own weather systems in the vacuum of space. Though space itself has no weather, some moons generate their own atmospheric phenomena that behave remarkably like terrestrial weather patterns. Io's volcanic eruptions create temporary atmospheres of sulfur dioxide that rise and fall with the volcanic activity, forming clouds and precipitation that rain back down to the surface. Triton has nitrogen geysers that create seasonal changes in its thin atmosphere, with nitrogen snow that sublimates and recondenses as the moon's distance from the sun varies. Even tiny Enceladus creates its own weather of sorts, with water vapor from its geysers forming temporary clouds before crystallizing and falling back to the surface like snow. These localized weather systems remind us that atmosphere and climate can exist on scales much smaller and stranger than planetary weather. Brief whispers of wind and precipitation in the cosmic void. Binary moons orbit each other while orbiting their planet. In the asteroid belt between Mars and Jupiter, many asteroids exist as binary pairs, two objects orbiting their common center of mass while traveling together through space. A few moons in our solar system show similar behavior on a smaller scale. Some of Saturn's tiny moons appear to be contact binaries, two objects that touch or nearly touch as they spin around each other. Others may be true binary systems with small separations, though the gravitational environment near a massive planet makes such arrangements less stable than in the asteroid belt. These moon systems within moon systems create complex orbital dynamics where tidal forces from the parent planet compete with the mutual attraction of the binary components, sometimes leading to eventual mergers or the ejection of one component into a separate orbit. Some moons have magnetic fields that paint auroras across alien skies. While most moons are too small to generate their own magnetic fields, Ganymede stands as a remarkable exception. Deep within its partially molten iron core, convection currents generate a magnetic field strong enough to deflect charged particles from Jupiter's powerful magnetosphere. When these particles do penetrate Ganymede's magnetic defenses, they create ghostly auroras that dance near the moon's poles, curtains of light shimmering in colors invisible to human eyes but detectable by spacecraft instruments. These auroras glow primarily in ultraviolet wavelengths, painting the thin oxygen atmosphere with ethereal patterns that shift and pulse with the rhythm of Jupiter's magnetic field. It's a light show performed for an audience of vacuum and ice, a reminder that even in the depths of space, electricity and magnetism can create beauty. The smallest moons tumble through space like cosmic dice. At the tiniest end of the size spectrum, moons become so small that their weak gravity can barely hold them together. These miniature worlds, often just a few kilometers across, tumble chaotically through their orbits with no preferred orientation. Unlike larger moons that become tidally locked to their planets, these cosmic pebbles spin freely, presenting different faces to their parent worlds with each rotation. Their surfaces are often covered in loose rubble and dust that shifts with each impact, creating landscapes that change over geological time. Some are so loosely bound that a major collision could shake them apart entirely, scattering their fragments into new orbits or allowing them to slowly reassemble under their own full gravity. They exist at the boundary between moon and asteroid, held together by forces so gentle that a strong breeze, if one could exist in space, might blow them apart. Tidal heating can melt moons from the inside out. In the gravitational embrace of giant planets, some moons experience forces so powerful they generate heat through constant flexing and stretching. This tidal heating occurs as elliptical orbits carry moons closer to and farther from their parent planets, causing the gravitational pull to vary in strength. The moon's interior rocks and ice are squeezed and relaxed like a cosmic stress ball, and this repeated deformation generates friction that can melt solid rock and ice. Europa's subsurface ocean exists because tidal heating keeps water liquid beneath the frozen crust. Io's spectacular volcanism is powered entirely by this process, making it the most volcanically active body in the solar system, despite receiving almost no heat from the distant sun. It's a demonstration of how gravity itself can become a source of energy, warming worlds that would otherwise be frozen solid in the outer darkness. Some moons have been turned inside out by ancient impacts. The early solar system was a violent place, filled with planetesimals and debris left over from planetary formation. Some moons bear the scars of collisions so massive they literally turn the worlds inside out, excavating material from deep within their cores and spreading it across their surfaces. The lunar highlands on our own moon may represent material blasted up from the deep interior during the period of heavy bombardment 4 billion years ago. Certain asteroids and small moons show spectroscopic evidence of having their deep, metal-rich cores exposed on their surfaces, suggesting impacts energetic enough to strip away their outer layers entirely. These cosmic excavations provide natural cross-sections through moon interior, allowing scientists to study materials that formed deep underground billions of years ago, now spread across surfaces under alien skies. Ring systems can give birth to new moons over millions of years. The relationship between rings and moons is more dynamic than it might appear, with each constantly influencing the other through gravitational interactions. Sometimes this process works in reverse from what we might expect, with ring material gradually coalescing to form new moons. Saturn's ring system may be constantly creating tiny moonlets that grow large enough to clear gaps in the rings, only to be torn apart again by tidal forces in an endless cycle of birth and destruction. Some of Saturn's small inner moons may have formed this way relatively recently in geological terms, condensing from ring particles over the past few million years. This ongoing process means that the moon systems of giant planets are not static arrangements frozen since formation, but dynamic environments where new worlds can still be born from the debris of their predecessors. The far side of our moon is a highland wilderness unlike anything on the near side. While we always see the same face of our moon due to tidal locking, the hidden far side remained a mystery until spacecraft first photographed it in 1959. What they revealed was a landscape dramatically different from the familiar near side, with far fewer of the dark volcanic plains called Maria, and instead dominated by ancient, heavily cratered highlands. This asymmetry tells a story of the moon's early history, when the near side faced Earth and received different heating and tidal forces than the far side. The far side's thicker crust prevented most volcanic eruptions from reaching the surface, preserving a more ancient landscape that serves as a window into the moon's violent early history. It's a hidden hemisphere that remained secret for all of human history, until the space age finally lifted the veil. Some moons are slowly being devoured by their parent planet's rings. The boundary between a moon and a ring system is not always permanent, and some small moons find themselves gradually losing mass to the very rings they help to shepherd. As these moons orbit within or near ring systems, Constant bombardment by ring particles slowly erodes their surfaces, stripping away material that then joins the rings themselves. This process can continue for millions of years, with the moon slowly shrinking as it feeds the ring system that surrounds it. Eventually, the moon may disappear entirely, completely cannibalized by the rings it once helped to maintain. It's a process happening in reverse around Saturn, where some of the inner moons may be the remnants of larger objects that have been gradually worn away by eons of ring particle bombardment, cosmic sculptures carved by the patient work of countless tiny impacts. Moon formation can happen in multiple ways throughout a single system. While our moon formed from the debris of a giant impact, the moons throughout the solar system tell stories of many different formation mechanisms. Some condensed from disks of material around their parent planets, much like miniature solar systems. Others are captured asteroids or comets that wandered too close to escape. Still others may have formed from ring material that gradually coalesced or split off from their parent planet during rapid rotation in the early solar system. Jupiter's 4 largest moons likely formed in place from a disk of material, while many of its smaller outer moons are clearly captured objects with retrograde or highly inclined orbits. This diversity of formation mechanisms means that each moon system tells a unique story of how worlds can come together through the patient work of gravity, collision, and chance. The surfaces of some moons record the history of the entire solar system. Because many moons lack atmospheres and geological activity, their surfaces preserve impact craters from billions of years of bombardment, creating natural archives of solar system history. By counting and analyzing these craters, scientists can determine not just the age of different surface regions, but also track changes in the population of asteroids and comets over geological time. The lunar surface, for example, shows evidence of a period of intense bombardment around 4 billion years ago, followed by a dramatic decline in impact rates. This record is preserved on airless moons throughout the solar system, each one a cosmic library where the story of planetary evolution is written in craters and scarred landscapes. The oldest surfaces have been collecting impacts for so long that they're saturated with craters, new ones erasing older ones in an endless cycle of cosmic archaeology. Some moons experience seasons that reverse the flow of entire atmospheres. Triton's unusual retrograde orbit around Neptune creates seasonal effects unlike anywhere else in the solar system. As Neptune follows its 165-year orbit around the Sun, different hemispheres of Triton receive varying amounts of solar heating over periods of decades. This creates a slow breathing effect in Triton's thin nitrogen atmosphere, with the entire atmospheric circulation reversing direction as the seasons change. During Triton's southern summer, nitrogen ice sublimates from the southern polar cap, thickening the atmosphere and driving winds toward the cooling northern hemisphere, where the gas condenses again as frost. This process can transport the equivalent of several meters of nitrogen ice from one pole to the other over the course of a single season, reshaping the moon's surface through a kind of atmospheric migration that unfolds over human lifetimes. Synchronous rotation creates permanent twilight zones on some moons. Many moons are tidally locked to their planets, meaning they always keep the same face pointed toward their parent world. This creates distinct regions on the Moon's surface that experience very different lighting conditions. The hemisphere facing the planet experiences regular day-night cycles as the planet itself rotates and reflects sunlight. The opposite hemisphere faces permanently away from the planet toward the stars. But between these regions lies a narrow twilight zone where the sun hovers eternally near the horizon, creating a landscape of perpetual dawn or dusk. These twilight regions experience unique thermal conditions, neither fully heated by direct sunlight nor completely frozen in shadow. On moons with thin atmospheres, these zones can create specialized environments where ice might be stable at the surface, or where chemical processes occur that would be impossible in the fully illuminated or completely dark regions. The smallest moons can be reshaped by single large impacts. When you're dealing with objects only a few kilometers across, a single impact can fundamentally alter the entire world. Many small moons and asteroids show evidence of impacts that excavated craters nearly as large as the objects themselves, creating landscapes dominated by single massive scars. Some impacts are energetic enough to shatter a small moon entirely, creating a rubble pile that slowly reassembles under its own weak gravity into a new configuration. These reformation events can happen multiple times over a small moon's history, with each major impact potentially scrambling the arrangement of surface features and internal structure. The result is that the smallest moons often have the most chaotic and unpredictable landscapes, where a single crater can span half a hemisphere, and the effects of individual impacts remain visible for billions of years. Some moons have polar ice caps that never see sunlight. In the deep craters near the poles of several moons, permanent shadows create some of the coldest environments in the solar system. Our own moon has such regions where temperatures remain below 40 Kelvin year-round, cold enough that water ice deposited there by comet impacts can remain stable for billions of years. These polar ice deposits act as natural freezers, preserving not just water, but potentially other volatile compounds that should quickly sublimate away in sunlight. Recent missions have confirmed substantial water ice deposits in these lunar cold traps, resources that represent both a record of early solar system chemistry and potential supplies for future explorers. Similar permanently shadowed regions exist on Mercury and potentially on other airless worlds, creating pockets of primordial ice in some of the most unlikely locations in the solar system. Ring moons can create spiral density waves that propagate for thousands of kilometers. The gravitational influence of moons on planetary ring systems creates some of the most beautiful and mathematically precise structures in the solar system. When a moon orbits near a ring, its gravity creates spiral density waves that propagate through the ring material like ripples on a cosmic pond. These waves can travel for thousands of kilometers, creating elegant spiral patterns that compress and rarefy the ring particles in mathematical harmony. The Cassini spacecraft revealed that Saturn's rings are filled with these spiral structures, each one tracing back to the gravitational influence of a specific moon. Some waves are so tightly wound, they create hundreds of spiral arms, while others form loose, open patterns. These density waves not only create beautiful structures, but also transport energy and angular momentum through the ring system, slowly evolving the orbits of both the rings and the moons that create them. Volcanic moons can create their own temporary ring systems. When volcanic eruptions on moons like Io are particularly violent, they can launch material at velocities high enough to achieve orbit around Jupiter. This creates temporary ring structures made of volcanic debris. Though these rings are typically short-lived, as the particles either fall back to the moon's surface or are swept up by Jupiter's powerful magnetosphere. Some of this ejected material can travel incredible distances, with sulfur and oxygen from Io's volcanoes detected throughout Jupiter's magnetosphere and even affecting the other Galilean moons. The process creates a kind of volcanic weather system that extends far beyond the erupting moon itself, demonstrating how the most energetic geological processes can have effects that ripple throughout entire planetary systems. Ancient impact basins on moons can focus seismic waves like cosmic lenses. The largest impact craters on moons create more than just holes in the ground. They fundamentally alter the internal structure of the world. These massive basins can act like seismic lenses, focusing earthquake waves that travel through the moon's interior. When moonquakes occur on the opposite side of our moon from large impact basins, the seismic waves can be focused and amplified as they pass through the fractured rock beneath these ancient scars. This focusing effect was discovered by the Apollo seismic networks, which detected unusually strong shaking in areas antipodal to major impact basins. The phenomenon suggests that the largest impacts in lunar history continue to influence the moon's behavior billions of years later, creating permanent alterations in the moon's internal structure that channel and concentrate energy from modern seismic events. Some moons are binary worlds masquerading as single objects. At the resolution limits of our telescopes, some objects that appear to be single moons are actually binary systems. Two objects orbiting each other so closely they appear as one. Contact binaries, where two objects actually touch while orbiting their common center of mass, create elongated moons with unusual rotation patterns. Other binary moons maintain small separations, creating complex dynamics where both objects are tidally locked, not just to their planet, but to each other. These systems can be unstable over geological time, with the components either gradually spiraling together to merge or being torn apart by tidal forces from their parent planet. The discovery of binary moons has revealed that the formation and evolution of small worlds can be far more complex than previously imagined, with gravitational interactions playing out on multiple scales simultaneously. The gravity of some moons is so weak, you could orbit them by running fast enough. On the smallest moons, surface gravity can be thousands of times weaker than Earth's, creating environments where the boundary between standing on the surface and orbiting becomes blurred. Deimos, Mars's smaller moon, has such weak gravity that a person could achieve orbital velocity simply by running at about 20 kilometers per hour and jumping at the right moment. This means that any impact energetic enough to kick up debris would launch that material into orbit around the moon, potentially creating temporary ring systems or causing the debris to eventually fall back down like extremely slow-motion rain. The walking and working conditions on such worlds would be unlike anything experienced on Earth, where every step could potentially become a small hop, and every thrown object might achieve orbit or escape velocity entirely. Tidal forces can turn moons into cosmic taffy pullers, stretching their shapes into ovals. When a moon orbits very close to its planet, the difference in gravitational pull between the side facing the planet and the side facing away becomes extreme enough to physically deform the entire world. The near side experiences stronger gravity and gets pulled toward the planet, while the far side feels weaker gravity and lags behind, stretching the moon into an elongated egg shape. This tidal deformation is constantly changing as the moon moves through its orbit, causing the surface to rise and fall like a slow, solid tide. On Io, this stretching and squeezing generates so much internal friction that it melts rock and powers the moon's spectacular volcanism. Even our own moon experiences this effect, with its surface actually flexing by several centimeters as Earth's gravity kneads its rocky interior like invisible hands working clay. Some moons have magnetic personalities that change with their orbits. Europa's interaction with Jupiter's powerful magnetic field creates electrical currents that flow through the moon's subsurface ocean, generating a weak magnetic field that pulses and shifts as Europa moves through its orbit. This induced magnetism acts like a cosmic lighthouse, with the magnetic signature changing in ways that reveal information about the hidden ocean beneath the ice. When Europa is closest to Jupiter, the magnetic field is strongest. When it swings farther away, the field weakens. These magnetic variations provided some of the first solid evidence that liquid water exists beneath Europa's frozen surface, as only a conducting fluid like salty water could generate the observed magnetic patterns. It's a case where invisible forces reveal hidden seas, magnetic whispers that speak of dark oceans beneath crystalline shells. Moon dust can glow softly in the darkness through electrical charging. On airless moons, the constant bombardment of charged particles from the solar wind creates static electrical fields that can make dust particles levitate and glow with a faint light. This phenomenon, called electrostatic dust transport, creates ghostly horizons where dust hovers above the surface in sheets and streamers that shimmer in the sunlight. Astronauts on the moon reported seeing a faint glow on the lunar horizon just before sunrise, possibly caused by electrically charged dust particles scattering sunlight. The effect is most pronounced in the boundary regions between light and shadow, where temperature differences and electrical charging create conditions for dust to dance in patterns invisible to cameras but clearly visible to human eyes. It transforms the surface of airless worlds into something slightly magical, where the ground itself seems to breathe with particles of light. Binary asteroid systems can evolve into moon systems through gentle collisions. Some of the most unusual moons in the solar system may have formed when binary asteroids, two rocks orbiting each other in space, were captured together by a planet's gravity. Over millions of years, tidal forces from the planet can cause these binary components to spiral closer together until they eventually touch in what amounts to the gentlest collision possible. Instead of shattering, the two objects stick together, creating contact binary moons with distinctive dumbbell or peanut shapes. These merged worlds often show clear evidence of their dual origin, with different compositions or surface features marking the boundary. where two separate worlds became one. The process demonstrates how cosmic violence can sometimes be surprisingly gentle, creating new worlds through embraces rather than explosions. Some moons experience ice ages that last millions of years. Just as Earth has experienced ice ages due to orbital variations, some moons undergo similar climate cycles on much longer timescales. Mars's polar ice caps grow and shrink over periods of hundreds of thousands of years as the planet's axial tilt varies, and this affects its two small moons as well. When Mars tilts more extremely, increased atmospheric activity can transport water vapor high enough to reach Phobos and Deimos, where it freezes onto their surfaces as frost. During less tilted periods, this ice sublimates back into space, creating a slow breathing effect where the moons accumulate and lose ice deposits over geological time. These moon ice ages are driven by the same orbital mechanics that affect planetary climate, but stretched across timescales so vast that entire species could evolve and go extinct during a single cycle. Shepherd moons can trade places in a cosmic shell game. In complex ring systems, small moons can actually swap orbits with each other through gravitational interactions, playing a kind of slow-motion cosmic shell game that unfolds over thousands of years. When two shepherd moons approach each other during their orbits, they can exchange energy and angular momentum, causing one to move to a higher orbit while the other drops lower. This orbital trading creates ever-changing configurations in ring systems, with moons periodically switching roles as inner and outer shepherds. Saturn's F-ring shows evidence of this behavior, with its shepherd moons Prometheus and Pandora occasionally coming close enough to perturb each other's orbits significantly. The process ensures that ring systems remain dynamic environments where the arrangement of moons and rings can evolve continuously over astronomical time. The smallest moons can be sculpted by the solar wind like cosmic sandblasting. On moons too small to hold onto loose surface material, the constant stream of charged particles from the sun acts like a gentle but persistent sandblaster, gradually wearing away exposed surfaces and redistributing material around the moon. This space weathering process can completely reshape tiny moons over billions of years, smoothing out sharp crater rims and creating the rounded potato-like shapes characteristic of many small satellites. The solar wind preferentially removes lighter elements, concentrating heavier materials at the surface and creating chemical gradients that vary with the moon's orientation to the sun. Some of the darkest surfaces in the solar system result from this process, as organic compounds are broken down and reformed into complex carbon structures that absorb almost all visible light. Resonant moons create invisible freeways that guide ring particles. The gravitational influence of moons in orbital resonance with ring particles creates what are essentially invisible highways in space, preferred paths where ring material can travel more easily. These resonant gaps and enhancements in ring systems aren't empty spaces or solid barriers, but regions where the probability of finding ring particles is either much higher or much lower than average. Particles that find themselves in these resonant zones can be either shepherded into stable orbits or quickly ejected, depending on the specific mathematical relationship between their orbit and that of the nearby moon. The result is that ring systems develop intricate structure on scales ranging from kilometers to thousands of kilometers, all organized by the invisible hand of gravitational resonance. Some moons are time capsules that preserve atmosphere from their planet's youth. Titan's thick nitrogen atmosphere may be a relic from the early solar system, when the sun was dimmer and conditions throughout the outer solar system were different. As Saturn and its moons formed, Titan may have captured and retained atmospheric gases that were common throughout the region, but have since been lost from other worlds. This makes Titan's atmosphere a kind of time capsule, preserving chemical conditions that existed billions of years ago when the solar system was young. Scientists study Titan's atmospheric chemistry, partly to understand what conditions might have been like on early Earth when life was first emerging. In this sense, studying moons can provide insights not just into alien worlds, but into the history of our own planet during epochs so ancient that no direct record survives on Earth itself. Captured moons can retain memories of their original homes in their mineral composition. When asteroids or comets are captured to become moons, they carry with them chemical fingerprints that reveal where in the solar system they originated. These compositional signatures act like cosmic passports, identifying moons that formed in the warm inner solar system versus those that condensed in the cold outer regions. Some of Jupiter's irregular moons show spectroscopic evidence of having formed near the orbit of Mars before being gravitationally scattered outward and eventually captured. Others appear to have originated in the Kuiper Belt beyond Neptune before somehow finding their way inward to become satellites of the giant planets. These captured wanderers represent a kind of cosmic mixing, bringing together materials from vastly different regions of the solar system into single planetary systems. Ring systems can act as cosmic laboratories for studying particle physics. The billions of ice and rock particles in planetary rings provide natural experiments in collective behavior, showing how vast numbers of objects interact through gravity and collisions on scales impossible to replicate in Earth-based laboratories. Ring particles demonstrate phenomena like self-organization, where local interactions between individual particles create large-scale structures like spokes, braids, and density waves. They also show how systems can maintain stability over geological time through a balance of competing forces, with gravitational shepherding by moons preventing the rings from either collapsing inward or dispersing outward. Studying rings has contributed to our understanding of everything from galaxy formation to the behavior of granular materials, making them valuable not just as beautiful celestial objects, but as natural physics experiments. Some moons generate their own aurora through interactions with cosmic rays. While most auroras are caused by charged particles from their parent star, some moons create their own light shows through interactions with high-energy cosmic rays from deep space. When these cosmic ray particles strike the thin atmospheres of moons like Ganymede or Europa, they can create brief, localized auroras that flicker and dance in patterns completely different from planetary auroras. These cosmic ray auroras are much fainter than those driven by stellar wind, often visible only in specific wavelengths and requiring sensitive instruments to detect. They represent a connection between the local environment of moon systems and the broader galactic environment. Reminders that even in the outer solar system, influences from distant stars and cosmic events continue to shape the behavior of small worlds. Moonquakes can be triggered by the gravitational pull of other moons. In complex moon systems like those around Jupiter and Saturn, the gravitational interactions between satellites can create seismic activity that has nothing to do with their parent planet. When moons pass close to each other during their orbits, the changing gravitational forces can trigger quakes in their interiors, especially if the moons have differentiated cores surrounded by more flexible mantles. These intermoon quakes tend to be small and infrequent, but they provide valuable information about the internal structure of moons and the strength of materials under the extreme conditions found in their deep interiors. The timing of these quakes can also reveal details about moon orbits and gravitational interactions to us that are difficult to measure through other means. The surfaces of icy moons can record the history of their parent planet's magnetosphere. On moons that orbit within their planet's magnetic field, the surface ice acts as a kind of geological recorder, preserving evidence of past changes in magnetic field strength and configuration. Charged particles trapped in the magnetosphere gradually alter the chemical composition of surface ice, creating patterns that reflect the long-term evolution of the magnetic environment. Europa's surface shows evidence of this process, with different regions displaying chemical signatures that correspond to different epochs in Jupiter's magnetic history. By studying these surface modifications, scientists can reconstruct how planetary magnetic fields have changed over millions of years, providing insights into the deep interior processes that generate these invisible force fields. Some moons have day-night temperature swings that would shatter rocks on Earth. On airless moons with slow rotations, the temperature difference between the sunlit and shadowed sides can be extreme enough to fracture solid rock through thermal stress. Our own moon experiences temperature swings of nearly 300 degrees Celsius between lunar day and night, causing surface rocks to expand and contract repeatedly until they eventually crack and crumble. This thermal weathering process gradually breaks down the lunar surface, creating the fine dust that covers much of the moon and giving it its characteristic gray appearance. On moons with even slower rotations or more elliptical orbits, these temperature variations can be even more extreme, creating landscapes where thermal stress is one of the primary geological processes shaping the surface over time. Binary moons can create complex eclipse patterns that last for days. When binary moons orbit each other while also orbiting their planet, they can create intricate eclipse patterns as they alternately pass in front of each other and cast shadows on each other's surfaces. These mutual eclipses can last for hours or even days, depending on the relative sizes and orbital periods of the two moons. During these extended eclipses, the shadowed portions of the moons cool dramatically, potentially causing atmospheric collapse or surface frost formation. The eclipse patterns can be so complex that they create seasonal effects even on moons with orbital periods of just a few days, with some surface regions experiencing regular cycles of heating and cooling that drive weather-like processes in the thin atmospheres or surface materials. Some moons act as natural particle accelerators, speeding up cosmic debris. Moons with strong magnetic fields can trap and accelerate charged particles to incredible energies, creating natural particle accelerators in space. Ganymede's magnetic field creates radiation belts similar to Earth's Van Allen belts, but concentrated around the Moon rather than a planet. These trapped particles spiral along magnetic field lines at speeds approaching a significant fraction of the speed of light, creating some of the most energetic radiation environments in the solar system. When these accelerated particles eventually escape or collide with the Moon's surface, they can create unique chemical reactions and surface modifications that don't occur anywhere else. Studying these natural accelerators helps scientists understand both the fundamental physics of magnetic confinement and the extreme radiation environments that exist throughout the universe. The ice shells of ocean moons may experience tectonic activity unlike anything on Earth. The floating ice shells that cover the subsurface oceans of moons like Europa and Enceladus can experience their own form of plate tectonics, with ice plates moving, colliding, and subducting in patterns driven by the liquid ocean below. This ice tectonics creates surface features like ridges, cracks, and chaos terrain that record the motion of ice plates over geological time. Unlike Earth's plate tectonics, which is driven by heat from radioactive decay and planetary accretion, ice tectonics on moons is powered primarily by tidal heating and the convective motion of the underlying ocean. The result is a completely different style of geological activity, where ice plays the role that rock plays on Earth, creating landscapes that are both familiar and utterly alien. Some moons have been turned into cosmic billiard balls by gravitational interactions. In the early history of moon systems, gravitational interactions between multiple satellites can lead to chaotic dynamics where moons are scattered into new orbits like billiard balls after a break. This process, called gravitational scattering, can completely rearrange moon systems over periods of millions of years. Some moons are ejected entirely, becoming independent objects or impacting their parent planet. Others are thrown into highly eccentric orbits that eventually decay through tidal interactions. Still others may be scattered into retrograde orbits or onto collision courses with each other. The current configuration of moon systems around the giant planets likely represents the stable end state of this early chaotic period, with only the survivors remaining in orbits that could persist for billions of years. Volcanic moons can export their geology to other worlds through particle ejection. The most energetic volcanic eruptions on Io can launch sulfur and sulfur dioxide particles at speeds high enough to escape not just Io's gravity, but Jupiter's gravity as well, sending volcanic material on trajectories that can reach other planets. Some of this ejected material may eventually fall to the surfaces of Jupiter's other moons, creating deposits of Ionian sulfur compounds on worlds hundreds of thousands of kilometers away. Over geological time, this process can significantly alter the surface chemistry of other moons in the Jovian system, making them partially volcanic worlds even if they have no volcanic activity of their own. It's a form of cosmic contamination, where the geology of one world slowly spreads throughout an entire moon system. The smallest moons can be completely resurfaced by individual asteroid impacts. For moons only a few kilometers in diameter, a single large impact can excavate and redistribute material over the entire surface, essentially giving the moon a complete makeover in a matter of hours. These global resurfacing events erase all previous geological history and create entirely new landscapes from the redistributed debris of the impact. The low gravity of small moons means that impact debris can travel completely around the world before settling back to the surface, creating complex patterns of ejecta deposition that can bury some regions while exposing fresh material in others. Some small moons show evidence of having been completely resurfaced multiple times throughout their history, each major impact creating a new chapter in their geological story, while erasing most traces of what came before. Resonant chains of moons can create musical harmonies in orbital motion. When multiple moons are locked in resonant relationships with each other, their orbital periods create mathematical ratios that correspond to musical intervals. The Galilean moons of Jupiter, for example, have orbital periods that create a kind of celestial chord, with Io, Europa, and Ganymede maintaining a precise 4:2:1 resonance that has persisted for billions of years. This resonant harmony prevents the orbits from becoming chaotic and helps maintain the stable configuration that allows each moon to exist in its own unique environment. Scientists have actually converted these orbital frequencies into audible sound waves, creating musical compositions based on the mathematical relationships between moon orbits. A reminder that the universe operates according to principles of harmony and proportion that human minds find inherently beautiful. Some moons experience reverse seasons where winter is warmer than summer. Due to complex orbital mechanics and tidal heating, some moons can experience seasonal temperature variations that seem backwards compared to Earth's seasons. When a moon's elliptical orbit brings it closer to its planet, during what would normally be its winter hemisphere, increased tidal heating can actually make winter warmer than summer. This effect is most pronounced on moons with very elliptical orbits around massive planets, where the difference in tidal heating between closest and farthest approach can overwhelm the seasonal effects of axial tilt and solar heating. These reverse seasons create unique climate patterns where ice may sublimate during winter and condense during summer, driving atmospheric circulation and weather patterns that operate in opposition to our terrestrial intuitions about how seasons should work. Ancient impact craters on moons can act as natural time capsules, preserving primordial materials. The largest and oldest impact craters on moons can excavate material from deep within their interiors, bringing ancient rocks to the surface that have remained unchanged since the moon's formation. These impact-exposed materials provide direct access to primordial compositions that would otherwise be buried beneath billions of years of surface modification. Some lunar craters have exposed rocks that are older than any surviving materials on Earth, offering glimpses into the chemical conditions that existed in the early solar system. The South Pole Aitken Basin on the moon's far side may have excavated material from the moon's mantle, providing the only direct access to the moon's deep interior composition. These impact time capsules preserve information about moon formation and early solar system chemistry, that would otherwise be lost to geological processes. Magnetic field interactions between moons and their planets can create invisible plasma tubes connecting the two worlds. When a moon with its own magnetic field orbits within its planet's magnetosphere, the interaction can create flux tubes of plasma that physically connect the moon to its parent world. These invisible bridges carry electrical currents and charged particles back and forth between the planet and moon, creating a kind of electromagnetic umbilical cord. Io and Jupiter are connected by such a flux tube, which carries over 1,000,000 amperes of electrical current and creates aurora displays on Jupiter's surface directly below Io's orbital path. These plasma connections can transport material and energy across hundreds of thousands of kilometers of space, demonstrating that the relationship between planets and their moons can be far more intimate and dynamic than simple gravitational attraction. Moon dust adhesion can create temporary atmosphere-like effects through electrostatic levitation. The extremely fine dust on airless moons can become electrostatically charged through interactions with the solar wind and cosmic rays, causing it to levitate above the surface and create temporary clouds that behave somewhat like a thin atmosphere. These dust clouds can scatter sunlight, creating optical effects like halos and strange lighting conditions that vary with the electrical environment. During lunar eclipses, when the moon passes through Earth's magnetic tail, changes in the electrical environment can cause these dust clouds to grow and dissipate in patterns that create visible changes in the lunar surface brightness. The phenomenon suggests that even airless worlds can have dynamic, responsive environments that react to changing space weather conditions in ways that mimic atmospheric processes. Some moons have been captured so recently that they still retain heat from their original formation. The most recently captured moons in the solar system may still be warm inside from the energy of their formation or from the gravitational interactions that led to their capture. This internal heat can drive geological processes like outgassing, thermal expansion, and even limited volcanism on worlds that would otherwise be completely frozen. Recent captures can be identified by their highly eccentric or inclined orbits, which haven't yet been circularized by tidal interactions with their parent planet. These newcomers to moon systems provide insights into the ongoing dynamics of planetary capture and the thermal evolution of small bodies during the transition from independent asteroid to planetary satellite. Ring particle collisions around some moons create microscopic lightning that generates radiostatic. The countless collisions between ring particles around planets like Saturn generate tiny electrical discharges that produce radio waves detectable by spacecraft instruments. These microscopic lightning bolts occur when ice and rock particles collide at high speeds, creating brief electrical sparks in the vacuum of space. The collective effect of billions of these tiny discharges creates a background radio hiss that varies with ring density and particle collision rates. During meteor showers or other periods of increased collision activity, this radio signature can intensify dramatically, providing a way to monitor ring dynamics and particle interactions from great distances. It's electromagnetic evidence of the constant microscopic violence occurring within ring systems, where every collision creates a brief spark in the cosmic dark. The orbital evolution of moon systems can be dramatically affected by solar tides over billions of years. While planetary tides dominate the short-term evolution of moon orbits, solar tides can play an increasingly important role over geological timescales, especially for moons in wide orbits around their planets. As moons slowly spiral outward due to tidal interactions with their planet, they eventually reach distances where solar gravity becomes comparable to planetary gravity. At this point, solar tides can begin to compete with planetary tides, leading to complex orbital evolution that can result in moons being lost to their parent planets entirely. This process may explain the absence of large moons around Venus and Mercury, and could eventually affect the outer satellites of the giant planets over timescales much longer than the current age of the solar system. Some binary moon systems can undergo orbital decay that leads to spectacular collision events. When two moons orbit each other in a close binary system, gravitational wave radiation causes them to slowly spiral inward toward each other over millions of years. As they get closer, tidal forces begin to distort their shapes, and eventually they merge in a collision that can reshape both objects entirely. These binary moon mergers can create some of the most unusual objects in the solar system, with complex internal structures reflecting their dual origin and surface features that record the violence of their coalescence. The process is similar to the black hole and neutron star mergers that create gravitational waves detectable on Earth, but scaled down to much smaller objects and longer timescales. Subsurface oceans on moons may have complex three-dimensional circulation patterns driven by tidal heating. The hidden oceans beneath the ice shells of moons like Europa and Enceladus likely experience circulation patterns far more complex than Earth's oceans due to the unusual heat sources and boundary conditions in these environments. Tidal heating creates temperature gradients that vary with orbital position, driving circulation patterns that change over the course of each orbit. The solid ice shell above and rocky core below create unique boundary conditions that can support multiple circulation cells operating at different depths and timescales. These circulation patterns affect not only the transport of heat and nutrients within the ocean, but also the stress patterns in the overlying ice shell, influencing where cracks form and how geological activity is distributed across the moon's surface. Moon formation can create temporary rings that eventually collapse back to the surface. When a large impact excavates material from a moon's surface, some of the debris can achieve orbital velocity and form temporary ring systems around the moon itself. These moonlet rings are typically short-lived, lasting anywhere from thousands to millions of years before the particles either escape entirely or spiral back down to the surface. During their brief existence, these rings can create complex gravitational interactions with the moon's rotation and any existing satellites, sometimes ejecting material that becomes part of the planet's larger ring system. Evidence for these ancient moonlet rings may be preserved in the unusual distribution of crater ejecta on some moon surfaces, where patterns suggest that material was temporarily held in orbit before eventually returning to create secondary crater chains and unusual deposit patterns. Captured irregular moons can retain atmospheres from their original locations for millions of years. When asteroids or comets are gravitationally captured to become irregular moons, they sometimes bring with them thin atmospheres or surface volatiles from their original environments. These captured atmospheres can persist for surprisingly long periods, especially if the moon's orbit keeps it far enough from its planet to avoid atmospheric stripping by magnetospheric interactions. Over time, these alien atmospheres gradually evolve through sublimation, solar wind sputtering, and gravitational escape, creating unique chemical signatures that can reveal information about conditions in different regions of the early solar system. Some irregular moons may still retain trace atmospheres today, remnants of the environments they experienced during their journey from the outer solar system to their current homes around the giant planets. Tidal resonances can create standing wave patterns in the subsurface oceans of icy moons. The gravitational forces that cause tidal heating in moons like Europa and Enceladus also create complex wave patterns in their hidden oceans. These standing waves, similar to seiches in Earth's lakes, can have periods matching the moon's orbital resonances, creating regions where ocean currents are enhanced or diminished by constructive and destructive interference. The wave patterns can focus tidal energy into specific geographic regions, potentially explaining why geological activity like geysers and surface cracking tends to be concentrated in certain areas rather than distributed uniformly. These oceanic standing waves may also play a role in transporting heat and dissolved materials throughout the ocean, creating chemical gradients that could influence any potential biological processes in these hidden seas. Some moons experience aurora that paint their surfaces with colors invisible to human eyes. The interaction between charged particles and the thin atmospheres of certain moons creates aurora displays that occur primarily in ultraviolet and infrared wavelengths beyond human vision. These invisible light shows can be incredibly dynamic, with curtains of energy dancing across moon surfaces in patterns that shift with magnetic field changes and solar wind variations. Ganymede's aurora, for example, creates shifting patterns of ultraviolet light that move across its ice-covered surface as Jupiter's magnetic field rotates. The energy from these aurora can drive chemical reactions in surface ice, gradually altering the composition of the moon's outer layers and creating distinct spectroscopic signatures that reveal the history of magnetic field interactions over geological time. Binary asteroid captures can result in moon systems with synchronized but offset rotations. When a binary asteroid system is captured intact by a planet's gravity, the resulting moon system can exhibit complex rotational dynamics where both components remain tidally locked to each other, but not to their parent planet. This creates a situation where the two moons present the same faces to each other throughout their mutual orbit, but their orientations relative to the planet change continuously. The result is a kind of cosmic dance, where the moon system maintains its internal synchronization while slowly tumbling relative to the planetary system. These offset synchronizations can persist for millions of years, creating unique tidal stress patterns that can drive geological activity in ways completely different from single moons or planet-locked systems. Deep impact craters can create natural laboratories for studying shock physics under extreme conditions. The largest impact craters on moons preserve evidence of shock metamorphism and pressure-induced phase transitions that occur only under the most extreme conditions achievable in nature. These natural laboratories contain materials that have been subjected to pressures and temperatures far beyond what can be created in terrestrial experiments, providing insights into the behavior of matter under conditions similar to those found in planetary cores or during stellar collapse. The shock-modified materials in these craters can include high-pressure mineral phases that are stable only under extreme conditions, creating natural museums of exotic physics, preserved in the cold vacuum of space for billions of years. Magnetospheric interactions can create plasma rivers that flow between moons and their planets. The magnetic field lines connecting some moons to their parent planets can channel plasma flows that create invisible rivers of charged particles streaming back and forth between the two worlds. These plasma rivers can carry significant amounts of material and energy, effectively creating a form of atmospheric exchange between planet and moon, even across hundreds of thousands of kilometers of vacuum. The strength and direction of these plasma flows can vary with the moon's orbital position and the planet's magnetic field configuration, creating tidal effects in the ionospheres of both bodies. Some of these plasma rivers may even be visible as faint aurora trails that trace the magnetic connection between world and satellite. Rubble pile moons can experience internal avalanches during close planetary encounters. Moons that are loosely bound collections of debris, known as rubble piles, can undergo dramatic internal rearrangements when they pass close to their parent planet or experience strong tidal forces. During these events, the weak gravitational forces holding the rubble pile together can be overcome by tidal stresses, causing the internal structure to collapse and reform in a matter of hours or days. These internal avalanches can completely change the moon's shape, density distribution, and surface features, essentially creating a new world from the same materials. The process may explain why some small moons have surprisingly spherical shapes, despite their low gravity, as repeated internal avalanches gradually redistribute material into more stable configurations. Ancient moon collisions can create impact melt sheets that preserve records of early solar system conditions. When large impacts occur on moons, the energy released can melt substantial portions of the moon's crust, creating vast sheets of impact melt that cool and solidify over thousands of years. These impact melt sheets act as time capsules, preserving chemical and isotopic records of both the impacting object and the target moon at the moment of collision. By studying the composition of these ancient melt sheets, scientists can reconstruct the types of objects that were common in the early solar system and track how the population of impactors changed over time. Some impact melt sheets on the moon contain clues about the composition of Earth's early atmosphere, preserved in the chemistry of materials that were blasted into space during terrestrial impacts and eventually deposited on the lunar surface. Tidal flexing can create subsurface magma chambers in rocky moons that experience extreme heating. On moons like Io, where tidal heating is so intense that it melts rock, The subsurface can develop complex networks of magma chambers and conduits that dwarf any volcanic system found on Earth. These subsurface magma bodies can exist in a state of constant flux, with new chambers forming and existing ones draining or cooling as the patterns of tidal hidden shift with orbital variations. The resulting volcanic systems can remain active for millions of years, constantly resurfacing the Moon and creating some of the most dynamic landscapes in the solar system. The subsurface architecture of these tidally heated worlds may be more liquid than solid, with vast underground oceans of molten rock that occasionally break through to the surface in spectacular eruptions. Some moon surfaces record the changing magnetic history of their parent planets through particle bombardment patterns. The surfaces of moons that orbit within their planet's magnetosphere bear invisible scars from billions of years of charged particle bombardment, creating chemical and isotopic patterns that record how the planetary magnetic field has evolved over geological time. During periods when the magnetic field was stronger, the Moon's surface received different types and intensities of radiation than during periods of magnetic weakness or reversal. These bombardment histories are preserved in the altered chemistry of surface materials, creating a kind of magnetic tape recording of planetary magnetic field evolution. By studying these patterns, scientists can reconstruct the magnetic history of planets over timescales much longer than any direct magnetic field measurements. Retrograde moons can experience unique seasonal effects as they orbit backwards through their planet's magnetosphere. Moons with retrograde orbits encounter their planet's rotating magnetosphere in a fundamentally different way than prograde moons, experiencing changing magnetic field orientations and plasma conditions that create unusual seasonal variations. As a retrograde moon moves through its orbit, it experiences the planetary magnetosphere as if it were moving against a rotating magnetic propeller, creating complex interactions that vary with orbital position and planetary magnetic activity. These interactions can drive atmospheric escape, surface charging, and even temporary aurora that follow patterns completely different from those seen on normally orbiting moons. The result is that retrograde moons exist in magnetic environments unlike anywhere else in their planetary systems. Volcanic outgassing from active moons can seed entire planetary magnetospheres with exotic chemistry. The volcanic emissions from moons like Io don't just affect the immediate vicinity of the eruption, but can populate entire planetary magnetospheres with sulfur, oxygen, and other volcanic gases that create unique plasma chemistry throughout the system. These volcanic contributions can dominate the chemical composition of the space environment around giant planets, creating conditions that affect all the other moons in the system. The volcanic gases can also interact with the planet's own atmosphere and magnetic field in complex ways, creating feedback loops where lunar volcanism influences planetary atmospheric dynamics and magnetic field behavior. Over geological time, this process can significantly alter the evolution of entire planetary systems. Moon-planet tidal interactions can gradually transfer rotational energy and alter planetary spin rates. The same tidal forces that cause moons to spiral outward from their planets also transfer angular momentum from the planet's rotation to the moon's orbital motion, gradually slowing the planet's spin over billions of years. This process has significantly affected the rotation rates of all planets with substantial moons, with Earth's day lengthening by about 23 hours since the moon first formed. For planets with many large moons, this tidal breaking can be even more dramatic, potentially slowing planetary rotation to the point where the planet becomes tidally locked to its largest moon. The process works in reverse for retrograde moons, which actually speed up their planet's rotation while spiraling inward toward eventual destruction. Binary moon systems can undergo chaotic orbital evolution that leads to moon ejection or collision on unpredictable timescales. When two moons orbit each other while also orbiting their planet, the three-body gravitational dynamics can become chaotic, meaning that tiny changes in initial conditions can lead to dramatically different outcomes over time. This chaotic behavior makes it impossible to predict the long-term fate of binary moon systems, with some lasting billions of years, while others break apart or collide within millions of years, despite having very similar initial conditions. The chaotic nature of these systems means that the current configuration of binary moons represents just one possible outcome from a vast range of possibilities, and that the moon systems we observe today may be fundamentally unpredictable survivors of an originally much more diverse population. Subsurface ocean circulation on icy moons may be driven by chemical gradients as well as temperature differences. The hidden oceans beneath the ice shells of moons like Europa and Enceladus may experience circulation patterns driven not only by temperature variations from tidal heating, but also by chemical gradients created by interactions between the ocean and the rocky core below. As water interacts with the rocky sea floor, it can become enriched in dissolved minerals and salts, creating density differences that drive circulation even in the absence of temperature gradients. These chemically driven currents may be particularly important in regions far from the main zones of tidal heating, where temperature-driven circulation is weak. The resulting complex circulation patterns could create chemical microenvironments within these oceans that vary dramatically in composition and potentially in their suitability for supporting life. Some moons may have formed from the collision debris of earlier moon generations that were destroyed by tidal forces. The current populations of small moons around the giant planets may represent the third or fourth generation of satellites in these systems, with earlier generations having been destroyed by tidal forces, impacts, or orbital instabilities. When a moon spirals too close to its planet and crosses the Roche limit, it can be torn apart by tidal forces, creating a ring of debris that may eventually re-aggregate into new, smaller moons farther from the planet. This process of destruction and reformation may have occurred multiple times throughout the history of the solar system, with the small inner moons of the giant planets being relatively young objects formed from the debris of their predecessors. Each generation of moons carries forward some memory of earlier generations in the form of compositional mixing and orbital dynamics. And now, as we drift toward the end of our gentle journey through these moonlit worlds, let your thoughts settle like dust on an airless surface, soft and still. We've wandered together through oceans hidden beneath ice, walked across landscapes painted with volcanic fire, and listen to the quiet songs that moons sing as they dance around their distant suns. Each of these celestial companions carries its own story, its own quiet mysteries, written in craters and cracks, in the rhythm of tides and the whisper of thin atmospheres. Tonight, as you rest, remember that above you moves our own faithful moon, slowly drifting away at the pace of growing fingernails, keeping time with the ancient waltz of gravity and motion that connects all these wandering worlds across the cosmic dark.